GATE 2024 Mechanical Metallurgy. So the figure shows a dislocation loop with Berger vector is B bar. Berger vector is given as B bar and identify the nature of dislocation at PQR. Dash dot lines show the horizontal and vertical diameters of the loop and the arrow shows the dislocation loop. So here at R bar, B bar and R bar is parallel. So R is screw. At Q, it is mixed because it is at a separate angle. So here it is perpendicular, it is edge dislocation. So P is edge and R is screw. Q is mixed. Answer is A. Match the concepts listed in column 1 with phenomena listed in column 2. The Pierce-Navarro equation, uh, the Pierce-Navarro stress tells us it involves dislocation glide. It is a force needed to move a dislocation within a plane of atoms in a unit cell. The Cottle atmosphere is tells you about the pinning of atoms by carbon and nitrogen. So it is yield point phenomena. The Paris law corresponds to fatigue. It is a crack growth equation that gives the rate of growth of fatigue crack. The considered criteria is onset of necking. It is the type of instability during tensile deformation where the cross-sectional area of the sample decreases by a greater proportion than the material strain hardens. It is 4, 3124. A single crystal is oriented such that the normal to the slit plane makes an angle of 60 degrees to the tensile axis. And now the critical result shear stress is. So the tensile stress at which the plastic deformation comments can be calculated by using Schmidt law, where the resolved shear stress is a product of applied stress and orientation factor. So typical CRS is equal to sigma applied into cos phi into cos lambda. The cosine of angle between slip and plane normal in the tensile axis is multiplied by cosine of angle between slip direction and tensile axis. So it is sigma applied equal to the 2 MPa by cos phi is cos 60 into cos 45, which is equal to 5.65. The tensile stresses at which the plastic deformation commences is approximately 5.7. So if this is the, when you apply stresses here, this is the angle at which the slip is normal to the tensile axis, the normal direction of the slip plane, making an angle lambda with the tensile axis. And this is the direction along which the slip direction is occurring. An isotropic material of a cuboid block is given by has a coefficient of linear thermal expansion alpha, Young's modulus E, and Poisson's ratio nu. The dimension of the cuboid are A, B, C, X, Y, Z. It rigidly constrained against expansion in X direction. However, it is free to expand in Y and Z direction. It is initially stress-free. Subsequently, it is heated so that its temperature increases by delta T. What would the change in the dimension be in the cuboid in Y direction? Assume linear elasticity that the thermal as well as mechanical stresses are infinitesimally small. This is a very important question. Conceptually, it is a very good question. Many of them have not explained this also. So, given the rod is rigidly constrained against the expansion in X direction, heating it won't cause any expansion in X direction. So, Ex is equal to Em plus thermal is equal to 0. We know Em is equal to minus E thermal, which is equal to minus alpha delta T because it is minus delta L by L in X direction. And now you know Ey equal to the nu of Ex, which is equal to nu of alpha delta T. So Ez is equal to the same way It is minus nu of Ex equal to nu of alpha delta t. So the total strain in y direction is strain due to y plus strain due to this x direction, which is minus nu of Ex. So it is totally alpha delta t plus nu alpha delta t, which is equal to uh, uh, 1 plus alpha into delta t. So Ey is given as this way. So you know delta b by b. So delta b is equal to b into 1 plus alpha into delta t. So answer is, sorry, nu into alpha delta t. This is b. Which one of the following surface the graph represents the Griffith criteria for the growth of crack in a brittle isotropic infinitely large flat with a center crack. This is a one of very good question conceptually which is given. Even many of them will make mistakes in these type of questions. The graph delta SC is the magnitude of total strain energy released, and the total surface energy is given by tau s. The AC is the critical crack length at which the crack growth starts growing. The tangent to delta SC curve parallel to tau S line is shown by dotted line. So if you'll see the total strain energy released for unit volume, total strain energy is given by minus sigma square by 2E into pi A square. So you want the magnitude of total strain energy, which is equal to sigma square by 2 into pi A square. So it is an upward parabola. So the shape will be symmetric that opens upwards. So you know that SC will be upwards. Now, the strain liberated by a crack growth, the strain energy liberated by a crack growth for forming a crack, the bonds must be broken, and then the bond energy is in effect absorbed by the material. So the total surface energy is given by 2 gamma A, which is the energy associated with the crack length. These two factors, if you'll consider tau s is a straight line. So this straight line will be like this. And now the um, crack length of 2A, these two surface free energies, these two free surfaces have been formed. As I've shown in the figure, the total energy associated with the crack is the sum of positive energy and the absorbed to create a new surface. The strain energy liberated by allowing the regions near the crack flows. So at the tangent the tangent at the point A, this is a critical crack where the propagation changes, the total surface energy changes. So this is the tangent at which the crack the critical crack growth is mentioned. So this will be the option D. Here you should see that the critical crack length is the point. This is not the point of the critical crack length. This is the point of critical crack length. At this point, both are same, like sigma square 2E and pi A square equal to tau SH or 2 gamma A. The creep test for a pure polycrystalline metal is performed in tension, and uh, and the creep strain rate is observed to decrease the during the primary stage. Then the creep mechanism is later determined by to be the dislocation climb controlled. The observed decrease in creep strain rate is due to. Now, if you'll see the primary stage of creep, the primary stage of creep is characterized by decreasing creep of strain rate. So primary is nothing but E strain rate decreases. So if you'll see E dot versus T, For the creep curve, it will be like this. For E versus T, curve will be like this. So if you'll see the primary creep rate, the creep rate strain rate decreases or creep rate decreases. For secondary, it's the lowest value or the lowest strain rate present, and it increases abruptly in the third stage. An increase in dislocation density, uh, so it is an increase in dislocation density during the creep. Dislocations are continuously multiplied through the various mechanisms. This initially lead to increase in dislocation density, contributing to higher strain rate. As the dislocation density increases, the this leads to uh, dislocation began to interact and impede each other, making further difficult for deformation. This work hardening gradually counters the increase in dislocation density, leading to decrease in strain rate. So this is the main reason. So if mechanism of dislocation climb, if you'll see, in a dislocation climb, the dislocations move out further from the move out of the allowing them to bypass obstacles and continuous gliding. This is sensitive to climb velocity, which depends on concentration of vacancies around the dislocation. The impact of dislocation density on dislocation climb. Higher the dislocation density, with the more dislocations present, there is an increased competition for the limited number of vacancies available for climb. So this reduces the average climb velocity of dislocation, ultimately leading to a decrease in overall creep strain rate. So grain growth, when a grain growth can occur during creep, it typically happens in later stages and has less significant impact on the primary stage compared to dislocation density. Decrease in dislocation density, this would contradict the observed phenomena increasing of work hardening wouldn't be consistent if dislocation climbed as a dominant mechanism. If decrease in dislocation density, increase in work hardening does not, they contradict each other. Increase in cross-sectional area, generally this does not impact the intrinsic creep rate per unit area. It would affect the fatigue properties of more is the exposed surface area, more will be the fatigue failure. So overall, the decrease in creep strain rate during primary for pure polycrystalline metal is with dislocation climb controlled with creep can be uh, attributing to the increase in dislocation density, and it's associated with the work hardening or effective climb velocities. A is the right answer. It's not for grain growth. This one. The steel bar is subjected to fatigue loading and tensile means. Uh, Given that the ultimate tensile strength is 1000 MPa, and now the fatigue limit under fully reverse loading is 250 MPa. The fatigue limit for a mean stress of 100 MPa, considering the Goodman relation is, in a Goodman relation, Goodman equation, if you see, sigma m by SU plus sigma A by SC equal to 1. Generally, this is used for finding out the fatigue analysis. So it is 100, mean is 100, and it is 1000 plus sigma. The fatigue limit is 250, and you need to find the alternating stress as 1. So 1 by 10 point 1.9. So sigma is 25 into 250 into 0.9, which is equal to 225 MPa. A larger rectangular component is fully reverse cyclic loading, and the component is known to grow the dominant fatigue crack from the outer surface. The stress amplitude sigma A is 100 MPa. The critical stress intensity factor is uh, given by 50 MPa root over meter. Then the crack length at which the component will fail catastrophically is. It's given fully reverse cycle. For fully reverse cycle, R is equal to -1. Okay. So fully reversed is nothing but sigma max equal to minus sigma min. So both tension and compression will be there and they will be equal. So sigma amplitude is nothing but sigma max minus sigma min by 2, which is equal to sigma max plus sigma max by 2. So it is sigma max is equal to 100. You got to know it is 100. So delta K is given. So delta sigma is equal to root over pi C. It is equal to 50 is equal to 100 into this safety factor is also given. The traditional geometric factor is also given 1.12 into root over pi into C, which is equal to 0.5 by 1.12 1 by pi whole square equal to C. The C is equal to 0.0634 meters. So you need it in millimeters, it is 63.4 millimeters. Thank you.